flash drum is an equipment that separates liquid into two phases, which is a vapor phase enriched in the more volatile components and liquid phase enriched in less volatile components. The system is called flash distillation because the vaporization is extremely rapid after the feed enters the drum. Did you know that the flash drum can be a vertical or horizontal vessel? Okay everyone, do you understand what is flash drum? Now, let's move it on to the working principle of the flash drum. Okay everyone, now let's see how the flash drum is working. First, the feed, which can be a mixture of constituents in liquid phase or in partially vapor liquid phase, is heated in order to increase its temperature. Then, a high temperature and pressure feed is flashed into a drum, which causes its pressure to reduce as it flows through a restriction valve at the inlet of the drum. The purpose of the restricted valve is to partially vaporize the feed passing through it. If the feed is a liquid mixture, then vapors are produced, and if partially vaporized feed is passed through the valve, then more vapors are produced. The sudden expansion is irreversible and occurs at constant enthalpy because if it were a reversible expansion entropy, it will be conserved. Lastly, gas is drawn off the top of the drum through a control valve whose steam position is set by a pressure controller. Liquid comes off the bottom of the tank on level control. Do you know there are several assumptions that can be made to flash drum, which are: first, adiabatic condition where no heat losses are assumed. Second, the density of the liquid in the tank is assumed to be a known function of temperature and composition. Last but not least, the density of the vapor in the drum is a known function of temperature, composition, and pressure. If the perfect gas law can be used, the equation shown in this video is used, where My is the average molecular weight of the gas, where Mj is the molecular weight of the component.
Hello and welcome to our presentation. My name is Rajiv Muhammad Imran, and together with my friends Nurul Khairia and Muhammad Shafiq, we will be explaining the multi-component flash drum and its steady-state model. The steady-state model is the simplest model of the multi-component flash drum. It is a model that neglects dynamics completely and the pressure is assumed to be constant. It also has no change of parameters with time, which means the d rho over dt, the total continuity equation, the d rho Vx over dt times the molecular weight, the component continuity equation, and dE over dt, the energy equation, is all equals to 0. The diagram shows the basic working principle of a flash drum. The feed, which is in liquid, will be flashed into a drum whereby the top product will be in gas phase while the bottom product will be in liquid phase. To develop the total continuity equation, first we must start with the general equation, which is the time rate of change mass inside the system is equals to mass flow into the system minus the mass flow out of the system. In order to obtain the correct unit, the density must be times with the volume and divided with time to obtain the correct unit. After that, we can develop the TCE, whereby the mass flow into the system is the initial density times with the feed flow rate minus the mass flow out of the system, which is the feed flow out of liquid times with its density, and also the feed flow out of gas times with its density. Due to it being a steady state model, the d rho over dt is equals to 0. Thus, the final TCE equation can be obtained.
We are proceeding with component community equation, which is CCE. The general equation for CCE, which as you can see in the slide, is the time rate of change mole with jet component inside the system is equal to mole of jet flow into the system minus with the mole of jet flow out of the system. A usual unit for this CCE is mole over time, where unit of rho is kg per meter cube, V is meter cube, molecular weight is kilomole over kilomole, time is 1 over time, and mass is x, which is kilomole over kilogram. And the final unit will be kilomole per time, which it is the same as what we want. So the equation of CCE is same as TCE, where d rho Vx dx over dt times with the molecular weight is equal to rho naught f naught times with x rho j minus with the rho L fl times the xj plus with the rho v lv times the yj. In this case, d rho v x over dt molecular weight is zero due to the steady-state condition. Make sure the equation is all divided by the average of molecular weight of every component which coming in and out of the system. Let's say we have a component Xa, Xb and Xe, so we have to find the average molecular weight for all the components of it. Final equation for CCE would be rho naught F naught over molecular weight naught average times with the X naught J is equal to rho LFL over molecular weight L average times the Xg plus with the rho V FV over molecular weight average of V times with the Yg. Next, for the energy equation, the equation is going to be d rho v h naught over dt is equal to h naught rho naught f naught minus h rho L fl plus h rho v fv, where in this case, the d rho vh naught over dt is equal to 0. And we are assuming this is in the liquid phase due to the H naught there. And the equation will be H naught rho naught F naught is equal to H rho L FL plus capital H rho V FV, where capital H is equal to CPT plus lambda V and H naught is equal to Cp naught T naught. We all notice that the capital H is for vapor phase and H naught for liquid phase. To find the vapor-liquid equilibrium when y is in the function of x, t, and p, in order to find the x, Rock's law is used where the equation is p solution is equal to p solvent times with the x solvent. After that, we use Antoine's equation, which log tan P is equal to A minus B over T plus with C to determine the pressure, while Dalton's law is used to decide the partial pressure. After solving all of that, we can finally obtain the equilibrium constant, which is K value by the using Kj is equal to Yj over Xj, with assuming it is behave ideally.
So this is one of the example of a steady-state model in a multi-component flash drum. So a flash drum is used to separate titanium and tin from a feed stream F, which also contains propane and methane. The feed composition entering the flash drum is given in Table 1. The resulting vapor and liquid streams are withdrawn at the rate of P and L moles per hour respectively. The mole fractions of the components in the feed, vapor, and liquid are designated by Zi, Yi, and Xi respectively. The flash drums operate at 15,200 mmHg and 50 degrees Celsius, assuming vapor-liquid equilibrium and steady-state operation, whereby the equilibrium relation is Ki equals Yi over Xi. Material balance phase equilibrium equations for a flash evaporator can be formulated as follows. So, Table 1 shows the composition of every component in the flash drum and Antoine equation constants. In the first question, in this example, is to calculate the percent of total P at 50 degrees Celsius that is evaporated. For example, V over F using secant or false position method. The next question is to determine the corresponding mole fraction in the liquid and vapor streams for 15,200 mmHg. So here is the steps to answer the first questions. The hint given, which is V over F, is actually the fraction of evaporated. The first step is to calculate the P saturation and Ki for each component. From the data given in the table 1, P sat is calculated by using the Antoine equation as shown in the slide, while Ki is calculated by using the formula P sat over P as shown in the slide. Next, the alpha is determined by using false position method. The iteration is started by using two initial guesses, which are 0.5 and 0.8.
The total feed evaporated can be calculated by using the equation that's shown in the slide. The value of Ki that has been calculated in the previous slide is used in the equation. Both initial gases of alpha are used in the vector balance equation. The next alpha, or the alpha n plus 1, is calculated by using the equation shown beside of the table. The iteration continues until function of alpha is equals to 0. Thus, it is calculated that the alpha, or the vapor to feed ratio, is 0.7006, and the percentage of the total feed evaporated is 70%, 70.006%. For question B, the mole fraction in the liquid and vapor streams need to be determined. From the previous calculation of Ki and alpha, which is 0.7006, the mole fraction of liquid for each component Xi are determined. The Xi can be calculated by using the equation in the slide, and from the calculated value of Xi, the Yi, or the mole fraction of vapor for each component, can be determined. The Yi is calculated using the equation stated in the slide. So that's all from Group 2. Thank you for listening, and we hope that you had fun and have a good day.
Assalamualaikum to all. So today we are group 3. We're going to present about multi-component flash drum rigorous model. So as well know, flash drum is quite a simple system. So that's why they made it into a multi-component flash drum. So how does a multi-component flash drum works? So first of all, multi-component will go through the feed, as we can see here, and then it will pass through a restricted valve. Okay, so you guys may be asking why it is needed to be flash. So the reason it needs to be flash is to reduce the pressure and in order to get it to bubble point condition. Okay, so in this system, it can be considered that no heat needed in flash drum. So as you guys can see, at the top part is the vapor component, while the bottom part is the liquid component. Okay, so let's go to the next slide. So basically, what is a rigorous model? Rigorous model is a very detailed model compared to the other two models, which are steady state model and also practical model. So as you can see on the slide, the top part is the main flash drum, while the below part is the rigorous model. So from this we can see that the rigorous model is more detailed compared to the main one. So at the rigorous model we can see that the vapor and liquid is being divided into two parts actually, and then we can see that PV and T prime is the component that that can be seen right after the liquid pass through the valve, and then the other 6 component we can see FV prime, rho V prime, YJ prime, and the other 3 on the bottom is right before it enter the inlet. Then we can see there is a line connecting the liquid into the vapor, which is called WV. WV is actually the rate of evaporation from liquid to vapor. Okay, since rigorous model is a more detailed system, we have to divide into 2 different set of equations. First one is liquid phase and the second one is vapor phase. As you can see from the figure above, for liquid phase, we have 1 inlet and 2 outlet. And then first thing first, we are going to compute the TCA. We are going to start with d rho L VL over dt equal to FL prime, rho L prime minus WV minus FL rho L. The unit for WV is kg per second since it's count as rate. Then as for the CCE, first of all, we start with rho dvxj over dt. So xj is actually the mole fraction for the system. So continue with the question. Rho dvxj over dt equals to fl prime xj prime rho l prime over mass weight average minus wvxj over mass weight average and minus fl rho l xj over mass weight average. As for the energy balance, the equation is dvl rho l hl over dt equal to rho l prime fl prime hl prime minus wvhv minus rho l fl hl. So in order to get the value of hl, the equation is hl equal to cpt, while for hv is hv equal to cpt plus lambda v. And lastly, in order to calculate the pressure of liquid, we can use Antoine's equation. Next, as for the vapor phase, it's basically the same as liquid phase. Just from the rigorous model on the right side, you can see that at vapor phase side, there are two inlets and one outlet compared to liquid phase, which have one inlet and two outlets. So first of all, we are going to compute the TCE for vapor phase, starting with d rho v vv over dt equal to fv prime rho v prime plus wv minus fv rho v. Next is our CCE. First one is rho v dv vyj over dt equal to fv prime yj prime rho over mass weight average plus wvyj over mass weight average minus fv rho v yj over mass weight average. For the energy equation, the formula is dvv rho vhv over dt equal to rho v prime fv prime hv prime plus wvhv minus fv rho vhv. So in order to get the value for hv, the formula is hv equal to cpt plus lambda v. And the last one is pressure of vapor. So to get the pressure of vapor, we use formula PV equal MRT, and we susun the formula to become P equal MRT over V. Driving force of evaporation can be found by using the formula WV equal KMT times P minus PV. So KMT is the constant of mass transfer between liquid and vapor, while P is the pressure at liquid system, while PV is pressure at vapor system. We have to keep in mind that the driving force of evaporation is due to pressure difference. So the value of pressure at liquid will always be higher than the pressure at vapor system.
I'm at outside. No choice. Life must go on. Okay, back to the objective of this presentation, which is rigorous model. Okay, rigorous model, it will follow the more details model. Okay, and then as we can see from the diagram, the first at the top one is the original diagram, and then after we apply the rigorous model, it will become like the below one, which is it have a splitter. Okay, in the splitter, at the top one we have the vapor feed, meanwhile at the bottom one we have the liquid feed. Okay, you can see the difference between the vapor feed and also liquid feed, which is at the vapor feed it will become F V prime and also rho V prime and YJ. Why do we YJ? Because it explains about the component J, and why F V prime rho V prime? Because V represents the vapor. Okay, then we move into the liquid feed. We can see that F prime L, rho prime L, and also X prime J. Okay, as I said before, L and V represents of the phase. Like V is vapor, meanwhile L is liquid. Okay, then why there is X and Y? X and Y represent for mole fraction of gas, meanwhile X represent the mole fraction for the liquid. And at the top one, that is the vapor feed, right? So why is the vapor feed is at the top? This is because the gas has low density, so it will appear on the top. Okay, and then as we can see, there is also a WV, which is represent rate of vaporization. Okay, in rate of vaporization, the liquid from the below will change into the vapor phase at the top one. Okay, next we will look into a question. Okay, the first one, at the left one, that is the original diagram, and then we use rigorous model and we get like the right one, which have splitter and also vapor and liquid feed. Okay, then the question asks for TCE, CCE energy and also energy balance for liquid and also vapor. So I'll be explaining about TCE, CCE and energy balance. Okay, for TCE, like I said before, there will be a boundary between the phase. So we can look at this diagram, which there is boundary between vapor and also liquid. Okay, then for the TCE, we know that TCE general equation is in minus out is equal to time. So we just input the information we get, which is we look at the diagram again and we just input the value inside the equation. The same things happen for the liquid phase and also vapor phase. But as we can see, in the vapor phase, there is 2 inlet and 1 outlet. Meanwhile, for liquid phase, there is 1 inlet and also 2 outlet. So for the sign of plus is for the inlet, while the minus 1 is for the outlet. Okay, next we will move into the CCE. CCE, the question asks for the vapor. So we will divide with the molecular weight average. Why do we divide with molecular weight average? This is because we use mole fraction, which is mole over mole, and the question need which is for mole per second. So we need to divide with molecular weight average. And moving to the energy balance, for the energy balance, we can see that the general equation, which is E in minus E out plus Q minus work shaft equal to dE over dt. But the thing is, there is no reaction, so we can assume the Q is, we can put 0 at the Q. Okay, and then we just do the same thing, which is input the equation E in minus E out plus Q and minus work shaft, and then we get the equation. And also we can also substitute the value. We know that HL equal to CPT and HV equal to CPT plus lambda V. So we can just substitute the equation, and like we can see it as the final answer. We substitute again the equation.
And now I will be explaining about one of the example of rigorous model. So as you guys can see here, the equation is liquid mixture of propane, isobutane, butane are fed to a flash drum at a reduced pressure PV. So by assuming the system is a rigorous model, proof energy balance for liquid phase as below, and also we need to state all the assumption. Okay, so for the solution, so first we need to state general energy balance equation as usual, and state the assumption, and such as potential energy is equal to 0, kinetic energy is equal to 0, and also there's no rate of reaction or generation, and also rho L and VL are assumed as constant. Okay, so for energy equation for liquids, as we can see here, the above, the below of the flash drum is the boundary condition for liquid phase. So for the energy in, we can say rho L prime, FL prime, and HL prime minus to WV, HL, and also minus to rho L, FL, and also HL. And then we stated that HL is equal to CPTL, and also rho L prime is equal to rho L. So from there we can substitute both of the equation to equation 1, and then we can get equation rho L prime times with FL prime CPTL, and also minus with WVHL, and also minus with rho L FL CPTL. Okay, so next we divided above question with rho L, VL, and CP, which equal to DTL over DT equal to FL prime TL over VL minus with WV HL over rho L, VL, CP, and minus with FL TL over VL, which can be a proof. Which can be proof. That's all. Thank you.
For the practical model, a more workable model is developed, and for this case, we exclude the vapor phase and we only write balance for liquid phase only. Therefore, since the practical model involved with liquid phase, so the liquid inlet stream, liquid outlet stream, and the rate of evaporation from liquid WV only involved in the equation. For the assumptions for the practical model, the first assumption is the vapor is always equilibrium with the liquid, and the second assumption is the vapor phase is too small or moving very fast, so we neglect the vapor phase.
Next, I will continue with all the equation. For the first equation is total continuity equation. The general equation is mass flow in minus mass flow out equal to time rate of change. So, the TCE for practical model is dVL rho L over dt is equal to rho naught F naught minus rho V FV minus rho L FL. The second equation is component continuity equation. The general equation is molar flow in minus molar flow out plus rate of formation is equal to time rate of change. So for the practical model, the CCE is dVL rho L xj over m liquid average over dt is equal to rho naught F naught x naught j over m naught average minus rho V FV yj over m average of vapor minus rho L FL xj over mass average of liquid. The third is energy equation. The general equation is total energy flow in minus total energy flow out plus heat added to the system minus work done by the system is equal to time rate of change of total energy. So, for the practical model, energy equation is dVL rho LH over dt is equal rho naught F naught H naught minus rho V FV H minus rho L FL H. Next, this is the available equation for practical model. So, the equation is VLE equation, the density equation for vapor and liquid, the average molecular weight equation, and the feedback controller equation.
So, balik pada kita punya practical model yang kita tunjuk contoh yang macam dengan cara nak kira lah. So, seperti yang kita lihat, dalam separation ni kita ada liquid dan vapor. Tapi dalam practical model ni, kita assume vapor is negligible sebab volume dia sangat sikit. Meaning, amount of liquid yang vaporize untuk jadi gas ialah sangat sikit dan we boleh assume dia sebagai kosong. Thus, dia akan jadi sama seperti week 11 kita punya tutorial 2 yang di mana kita neglect the vapor and only focus on the liquid phase only. So, bila kita fokus untuk liquid phase only, kita kan ada top product and bottom product. So, bila kita buat total component equation, so kita mesti kena buat total of this whole things tapi tak adalah spesifik. Contoh macam bila kita buat rigorous method, kita ada spesifik untuk liquid punya part dengan vapor phase punya part. But now we only focus on the overall part, which is the liquid only. So to get the TCE, we first the differentiation of volume time the rho over time, which is kalau kita potongkan unit dia, kita akan dapat V, which is meter cube, and rho is kg per meter cube. So bila kita potong, kita akan dapat lah kita punya benda yang kita nak, which is kg per second, kg per time lah. And sama seperti sebelah, which is rho kg per meter cube darab dengan flow rate, which is meter cube per second. Dan bila kita darab, kita akan dapat sama seperti sebelah, which is mass over time. So kita pergi kepada CCE pula, which is also kita focus on only on the liquid part, which is the volume. Sebab sama seperti yang sebelum ni, volume darab dengan density darab dengan, sebab kita ada komponen yang berbeza-beza. So yang ni kita buat komponen J. Apa maksud komponen J? Ialah contohlah, dekat sini kita ada XA dengan XB. So meaning dekat dalam liquid ni ada komponen, contoh ada aseton dengan ada benzin. So ni kita fokus dekat aseton saja. So contohlah VL rho L XA over molecular weight. Ini mass weight average. Mass weight average meaning dekat sini, contoh dekat ambil lah sini. Contoh dekat sini kita ada mass A, mass B, mass C. Kita kena tambah semua ni bahagi 3. So kita dapatlah mass weight average tersebut. Kemudian kita bagi kita tengoklah kita punya unit kat depan ni. Unit kat depan ni ialah meter cube darab dengan density, which is kg per meter cube over yang X ni mass fraction. Bila mass fraction tak ada unit. And then kita ambil kepada mass molecular average ni, which is kg per kmol. So bila kita potong, kita akan dapat kita punya unit kat sini ialah kmol per second, which is CCE kita nak dalam bentuk mol lah. So bila kita dah dapat unit tu, kita pergi kat sebelah pula, sama kita tengok unit dia, which is kita akan dapat juga kmol per second. And then cara yang kita dapat ialah kita ambil macam mana kita nak buat CCE lah, ikut je sama dengan TCE, cuma kita tambah sekali dengan dia punya komponen. Tambah komponen bahagi mass weight average. And then untuk energy balance pula, kita yang kita lihat, kita darab volume dia, density dengan dia punya enthalpy. Ini sama je seperti regress, cuma dia just lagi simple lah, sebab kita tak payah buat dua kali, and memang ada this equation saja yang kita kena guna. And kita akan dapat density F0H, density FVH, and density LFLH. Ni kenapa dapat 3 ni? Sebab kita ada input, kita ada output top, output bottom. So kita dapatlah 1, 2, 3. And then macam ni kita nak cari equation ni, macam rho V FV sama dengan work vapor. So sama dengan rho V FV. And then contoh kita nak dapat rho V pula, kita boleh guna equation of state, which is MP over RT. Itu saja. Semoga semua faham, dan jika ingin lebih memahami, bolehlah kita sama-sama belajar di kelas di masa akan datang. Terima kasih.
Okay, now we're going to learn about the batch reactor. So what is actually a batch reactor? Batch reactor is the simplest type of reactor vessels used for chemical or industrial processes, and it is very suitable for small volume and also expensive production, such as specialty chemicals and also pharmaceutical products. And batch reactor is suitable for slow reaction. So how does a reactant works? First of all, the reactants will be charged into the reactor, and then we will close the outlet valve so that the level of reactant inside the reactor is at our desired level. And the liquid inside the reactor is initially cold, so that is why we need to supply the steam into the reactor so that we can increase the T at our desired temperature. And that means that Q is added if the steam is supplied. And at some point, some of the reactant will start to condensate, and it will be trapped into the condensate part, which is here. And for example, if the reaction is exothermic, that means that we need to bring the temperature down. So that is why we need to supply the cooling water inlet and control the outlet and also inlet valve. Basically, we need to control the temperature inside the reactor, because based on what temperature the reaction needs to have. So basically, we need to control the temperature and also to know when the time when the reaction need to stop, so that we will get our desired products. For example, is A will produce B and B will produce C, and B is our desired product, C is our undesired. So if we let the reaction which is happen inside the reactor to go on too long, there will be much B converted to react and form C. So low yield of B will we will get low yield of B. And if we stop the reaction too early, then only small amount of A will be reacted to produce B, and hence low yield of B. So that is why we need to know the optimum temperature and also time for the reaction to stop, so that the reaction will favors to our desired product. There's a few conditions that we need to consider. The first one is if the dependency of T on both K1 and K2 is the same. So meaning that both of the reaction will have the same EA. So if this happen, then the reaction should be run at the highest T to minimize the batch time. However, we also need to remember that when the operating temperature is too high, it will degrade the product or reactants due to the high temperature. So meaning that we will not get the product that we want, or the product is not conform to the product quality that we desired. And also we also need to consider our maximum working pressure. For example is the batch reactor will have the jacket wall. So we need to know what type of material that we use for the reactor, so that it will not exceed the maximum pressure for the reactor. The second condition is if the K1 is more temperature dependent than K2, meaning that K1 is lower than K2. So we this one also the same. We need to run the process at the highest possible temperature to favor the reaction to B. But we also need to determine when to stop the reaction, so that the B won't convert into C via CCE and also energy balance, because the volume is constant in the batch reactor, so we don't need to use the product rule. The third condition is if K2 is more temperature dependent than K1. So meaning that we have A to B and B to C. K2 is dependent on T, meaning that if we change the T, the K2 also will change according to the T, because it is dependent to temperature. So if this happen, we need to start off at high temperature at first to get the K1 or reaction 1 to start and produce B, and then we need to drop the temperature to prevent the loss of too much B to produce C. So, how to know what is our optimum temperature and also time for us to get or stop the reaction? Alright, this is for example, if let's say we already calculate the TCE, CCE and also energy balance. As for the TCE, it is equal to 0 because the volume is constant. So for example, we already calculate the CCE energy balance for A, B and C. So and we also need to determine the components profile as a function of T profile by using the Euler's or also Runge-Kutta. Okay, so when we already have the components profile in function of T profile, we can plot it, and we will get the graph like this. And the energy balance also need to plot on the same graph. For example, if our T initial is 30 and then it start to increase, this is because we supply the steam. However, we cannot let the temperature too high because we don't want the product to degrade. So we also need to know when is the degradation of the product. And then from here we can see that the graph is starting to decrease. This is because we start to supply the cooling water. Alright, so when should we stop? How do we know when is to stop and what is the optimum temperature and also time, the resident times inside the reactor? Alright, for example, when we look at this graph, we can see that from here, when the CA, we can see that A is decreased, meaning that more A is react and produce B. So that's why B is increasing. But however, when it goes right here, we can see that B starting to decrease. This is because at here reactions start to happen and B starts to form C. So we don't want this to happen because our desired product is B and C is our undesired product. So we need to stop before the C is produced or C is formed more than B. So from here we can see that this is our T optimum. So at here T, meaning that this is our T optimum and this is our time for the reaction to stop. This also can call as the resident times. It is the same, T and also tau, the resident times.
For the energy equation for the process, the equation is rho V Cp dt over dt equals to negative lambda 1 V K1 Ca minus lambda 2 V K2 Cb minus Hi Ai in bracket T minus Tm, T meter. Next, the energy equation for the metal wall. For this energy equation, we assume it is a lump metal model. The equation is rho m Vm Cm dt over dt equals to H naught A naught in bracket Tj minus Tm minus Hi Ai in bracket Tm minus T.
Okay, so now we'll proceed with example 2. The question says that the oxidation of ethanol to form acetaldehyde is carried out in a batch reactor, but unfortunately, the acetaldehyde is also oxidized to form carbon dioxide. The reactions are irreversible and first order in ethanol and acetaldehyde, respectively, as follows. So, the volume of the reactor is constant, and the ratio of the inlet flow rate to the volume of the reactor is 0.25. The density of the solution is constant, given that with initial concentration of ethanol is 2 mole per liter and acetaldehyde is 0 mole per liter. The values of K1 and K2 are 1 per minute and 3 per minute respectively. By using the Euler method, simulate the concentration profile of component ethanol and acetaldehyde in the reactor at T equals to 0 to T equals to 0.4 minute with a step size of delta T equals to 0.2. The calculated values must be corrected to 4 decimal places, then plot an appropriate graph representing the concentration of ethanol and acetaldehyde in the reactor. Firstly, we have to generate the general equation of TCE and CCE. So, TCE, as you know, is the time rate of change of mass inside the system, which means that the mass flow into the system is subtracted with the mass flow out of the system. Next is the component continuity equation or CCE, which represents the time rate of change of moles of jth component inside the system, whereby it is equal to the flow of moles of jth component into the system minus with the flow of moles of jth component out of the system plus with the rate of formation of moles of jth component. So in step 2, since the volume of the reactor and density of the solution are constant, dV rho over dt equals to F naught rho minus F rho. So since the volume and density are constant, we cancel it out. So it is left with F naught equals to F. So in step 3, ethanol is oxidized to acetaldehyde and oxidizes to carbon dioxide. So firstly, we generate the CCE on component A, which is ethanol. So as usual, VdCA over dt equals to F naught Ca naught minus FCA minus VK1Ca. And we divide the whole equation with V. So we are left with this equation. And since, as mentioned before, F naught equals to F, the equation can be simplified as dCA over dt equals to F Ca naught minus Ca over V minus K1 Ca. And that is for CCE on A. As for CCE on B, the equation is V dCB over dt equals to F naught Cb naught minus FCB plus VK1 Ca minus VK2 Cb. dCB over dt equals to F naught Cb naught minus FCB over V plus K1 Ca minus K2 Cb. And as mentioned, since F naught equals to F, so the equation can be simplified as follows.
Next, we will proceed with step 4. First thing first, we are going to find the value of Ca and Cb at t equals to 0.2 minute. the first step is, at T equals to 0, our Ca and Cb value will be 2 mole per liter and another one is 0 mole per liter respectively. So, based on our CCE, we will insert all the values based according to the formula to the CCE, and then we calculate it and we will get the value of dCA over dt is equals to -2. Next, we will proceed to the dCB over dt. This is the same step, which we will insert all the values that we have, and then we will calculate it and we will get that dCB over dt is equal to 2. For the next step, step 5, we will use Euler's method equation, which is to determine the Ca and Cb value at t equals to 0.2 minute. The formula that will be used is Ca equals to Ca naught plus a dCa naught over dt times with delta t. The Ca1 will be 2 plus with -2, which is the value of dCa naught over dt, which we have calculated before, and times with 0.2, which is the value of delta t, which have been given by the question. After all the values have been inserted and calculated, the final answer will be 1.6 mole per liter for our Ca. Next, we will calculate the Cb, which is by using the same formula, and then we will insert all the values that we have and then calculate. We will get the value of Cb is equal to 0.4 mole per liter. Do take note that the value that we calculate, the Ca and Cb, is the value of concentration at the t equals to 0.2 minute. Next, for the step 6, we still use the Euler's method equation to find our Ca and Cb at t equals to 0.4 minute. So, we will firstly proceed with at t equals to the same value that we have at t equals to 0.2 as our Ca naught, and then the same formula, we will find the dCa over dt. We will insert all of the value that we have and then calculate it. We get the value of dCa over dt is equal to -1.5. For dCb over dt, we will still use the value of Cb naught is equal to 0.4 and insert it inside the formula and then calculate. After that, we will get the value of dCb over dt is equal to 0.5. Next, by using we continue with finding the second Ca value by using still the same formula, but using the newest value that we have, and that which is Ca, which is 1.6, and then the dCa over dt, the new one that we have calculated, which is -1.5 times with 0.2, and then we will get the value of 1.3 mole per liter. After that, we will calculate the Cb. So this is the same method, which we will insert our newest value for Cb, which is 0.4, and then the value of dCb over dt that we have calculated before, which is 0.5, and times with 0.2. After being calculated, we will get the value of Cb is equal to 0.5 mole per liter. Do take note that the value that we have calculated, Ca and Cb, is at t equal to 0.4 minute. That is all from me. Thank you.
Hi and Assalamualaikum. We are from Group 6. Today we are going to present regarding heating and cooling in batch reactor. Before we start, I would like to introduce our team members. Our team member consists of 3 people, which is Muhammad Izwan bin Saifuddin, Nurul Ashikin binti Safwan, and last but not least, me, Nur Afifah binti Hisham. Hi everyone, my name is Nur Afifah binti Hisham. Today I am going to talk about how heating and cooling happens in a batch reactor. As you can see, the figure above is the batch reactor sketch. So now, let's start. Reactant is charged into the vessel. Steam is fed into the jacket to bring the reaction mass up desired temperature. The steam is fed with the steam rate Fs having density ρS and enthalpy Hs. The steam is provide a heat in the reaction mass to bring the reaction mass to desired temperature. Then, the steam rate condense and it will be separated at the bottom of the jacket with a rate of condensation Wc and enthalpy Hc. Then, cooling water must added to the jacket to remove the exothermic heat of reaction and to make the reactor follow the prescribed temperature time curve. Then, the steam is stopped and cooling water fed the jacket with the flow rate Fj, density ρj, and temperature Tj note. The same flow rate of cooling water is out with the flow Fj and density ρj, but with different temperature Tj. This temperature profile is fed into the temperature controller as a set point signal. The set point varies with time. Next, first order consecutive fractions take place in the reactor as time proceeds. As you can see from the picture above, there are two reactions happening, which is at K1, A is the reactant and B is the product. Meanwhile, at K2, B is the reactant and C is the product. The product that we want to make is component B. If we let the reaction go on too long, too much of B will react to form undesired C. That is, the yield will be too low. But if we stop the reaction too early, too little A will have reacted and resulted the conversion and yield will be too low. Therefore, there is an optimum batch time when we should stop the reaction. This is often done by quenching it. But when to quench the process fluid? Before we start to quench the process fluid, we need to know there are three conditions that we have to consider. Number one, if the temperature dependence of the specific reaction rates K1 and K2 are the same, which means if their activation energies are equal, the reaction should be run at the highest possible temperature to minimize the batch time. This maximum temperature would be a limit imposed by some constraint, which is A, maximum working temperature or pressure of the equipment, B, further undesirable degradation or polymerization of product or reactants at very high temperature. The second condition that we can consider if K1 is more temperature dependent than K2. We again want to run at the highest possible temperature to favor to the reaction B. In both cases, we must be sure to stop the reaction at the right time so that the maximum amount of B is recovered. The second condition is if K1 is less temperature dependent than K2. The optimum temperature profile we again want to run at the highest possible temperature to get the first reaction going, but in both cases we prevent the loss of too much B. Figures in the slide shows so that the maximum temperature and concentration profiles. The second condition that we can consider if K1 is more temperature dependent than K2 be achieved, we again want to run at the highest possible temperature to favor to the reaction B. In both cases, we must be sure to stop the reaction at the right time so that the maximum amount of B is recovered.
Thank you, Afifa. For the next part, we start with heating phase. As Afifa explained earlier, heating phase is when steam is fed into the jacket to bring the reaction mass up to a desired temperature. The reaction is exothermic, since heat is released inside the jacket and there is a rate of condensation of steam leaving the reactor. And for the liquid condensate, it is assumed to be immediately drawn off through a steam trap. During heating, there are three equations may be needed, which are first total continuity equation, second is energy equation, and lastly equation of state for the steam. For this example, we are going through the first equation, which is total continuity equation. For the general equation for total continuity equation is mass flow of vapor steam into reactor, which is flow rate of the steam Fs with density of the steam ρs minus with mass flow of vapor steam out from the reactor, which represent the rate of condensation of steam Wc is equal to time rate of change of mass in reactor Vj d rho j over dt. The unit for both sides are in mass over time. The second equation is energy balance for steam vapor. For the general equation for energy balance is total flow of energy into the system minus with the total flow of energy out of system plus heat added to the system minus work done into the system equal to time rate of change of total energy inside system. For first is total flow of energy into the system, which is flow rate steam Fs with density of steam ρs with enthalpy of incoming steam Hs. Second is total flow of energy out of system in which exothermic heat of reaction was take place and there is a condensation occurs. When the reactor is heated with steam, Tj is bigger than Tm and Tm is bigger than T. The outside film coefficient HO also significantly different from for condensing steam. The result for rate of condensation is Wc with the Hc enthalpy of liquid condensate. Last, for the heating phase, there is equation of state can be developed. This equation is to calculate temperature Tj and pressure P from density rho J. The perfect gas law and simple vapor pressure equation can be used, where ideal gas law is equal to rho equal to mp over RT, where P can be used equation of vapor pressure from an untoist equation for water, which is Pj equal to exponent AW over Tj plus BW. I think that's all from me. Cooling phase will be continued by Izwan.
Thank you, Nur Ashikin. Next, I will continue with cooling phase. During the period when cooling water is flowing through the jacket, only one energy equation for the jacket is required if we assume the jacket is perfectly mixed. And this is the equation. The last term, which is circled in red color, is the endothermic reaction formula. And that's all from us. I hope you all understand what we explained in heating and cooling phase. Thank you so much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ismail bin Talib, and my others two member is Muhammad Aikal bin Zaid and Muhammad Firdaus bin Zakaria. Today, my group will present about some of the example of the batch reactor. So, for the batch reactor, there are no flow in and flow out in the batch reactor. So, basically, the TCE of the original TCE is time rate of change of mass inside the system equal to mass flow in minus mass flow out. So, back from the statement, we can cancel the mass flow in and mass flow out. So, the TCE equal to 0. So, the original CCE, time rate of change of mole component inside the system, equal to flow of mole of component into the system minus flow of mole of component out of the system plus rate of formation of mole. Same goes at the TCE. We cancel out the flow in and the flow out. So we get the time rate of change of mole component inside the system equal to rate of formation of mole component from chemical reaction. So we go to example. For example 1, A produce B. So with the reaction rate of K1. So for the TCE, we can conclude that flow in and flow out is none. So we have TCE equal to 0. So for the CCE, we have only for generation. So we got that VdCA over dt equal to negative VK1CA, because it negative because A is consumed in the process. So for the CC for component B, we got VdCB over dt equal to positive VK1CA, because component B is produced in this process. So we go next for the example 2. We got A produce B and B also produce A. So we got K1 and K2. So for the TCE, it's same because there is no flow in and flow out. So for the CCE of component A, we got VdCA over dt equal to negative VK1CA plus VK2CB. Negative VK1CA because A is consumed to produce B, and positive VK2CB is because B is consumed to produce A. So same goes for component B, but it vice versa. So we got VdCB over dt equal to VK1CA minus VK2CB, because in the process B is produced in K1 and B is consumed for K2. Next, we go for example 3. We got A produce B and B produce C. For this TCE, we got 0 because there is no flow in and flow out for batch reactor. For CCE for component A, we got VdCA over dt equal to negative VK1CA. In this process, A is consumed and not produced. For CCE for component B, we got VDCB over dt equal to VK1CA minus VK2CB. For CCE for component C, we get VDCC over dt equal to VK2CB because only at the K2, the C is produced by consuming B. Next, we go for more advanced example. Example 4, we got A plus 3B produce C. So, as always, TCE equal to 0. The CCE for component A, we got VDCA over dt equal to negative VK1CA CB power of 3. Component A is consumed, so we got the negative. So for the CCE for component B, we got VDCB over dt equal to negative 3 VK1CA CB power of 3. Also, the component B is consumed in this process. That's why we have the negative. And 3 is because they need 3 component of B. For CCE for component C, we got VDCC over dt equal to VK1CA CB power of 3. In this process, C is produced, so the sign is positive. Next, we go for more complicated example. So we got example 5, we got 3A plus 3B produce 2C and D. Same goes for the TCE, we got 0 because of no flow in and flow out. For the CCE for component A, we have VDCA over dt equal to negative 3VK1CA power of 3 CB power of 3. The negative sign because A is consumed in this process and 3 is 3 component A for is consumed. So for the CCE of component B is same, but this is component A and B. So we got both got 3 components, so it seems. So for the CCE for component C, got VDCC over dt equal to dVK1CA power of 3 CB power of 3. Positive because in this process, C is produced by consuming 3 component A and 3 component B. So for the CCE for component D, we got VDCD over dt equal to VK1CA power of 3 CB power of 3. The difference is C and D. The difference is C is produce 2 components and D is just 1 component. So next we go for example 6. We got A plus B produce C plus D, and also C plus D also produce A plus B. So we just go for the CCE. So we got for component A, we got VDCA over dt equal to negative VK1CACB plus VK2CCCD. Negative because A is consumed in the first process, and for the backward process, C and D is consumed to produce A and B. So A also produced in this process. So same goes for the CCE for component B. It's same because in process 1 for the K1, B is consumed, and for backward process, B is produced. So we got negative first and positive. So for the CCE for component C, we got VDCC over dt equal to VK1CACB minus VK2CCCD. It's just the same, but for the first process, C is produced from consuming A and B. And for the backward process, we got that C and D is consumed for produce A and B. That's why we got negative sign for the K2. Same goes for component D. We got VDCD over dt equal to VK1CACB minus VK2CCCD.
Okay, Assalamualaikum. My name is Muhammad Haikal bin Zaid, and I will be explaining regarding the example 1. But we will be focusing more on the reaction rate. As you can see here, there's reaction 1 and reaction 2. Both the forward and the backward reactions in the first reaction are of second order with respect to the reactants. Meanwhile, the second reaction is of first order. As you can see here, this is the general equation of TCE. This is because, as Ismail mentioned earlier, this TCE will be 0. So, in batch reactor, there is no flow in or flow out. So the CCE will be time rate of change of moles inside the system is equal to the rate of formation of moles. This is because we have already cancelled out the flow of moles into the system and the flow of moles out of the system. Okay, in this slide, as you can see, the TCE is equal to 0, and we need to find the CCE for each component. So CCE for component A will get negative V K1 F CACB plus with V K1B CC power of 2, and the final answer is negative K1 F CACB plus K1B CC power of 2. Meanwhile, the CCE for component B is equal to negative K1F CACB plus with V K1B CC power of 2, and the final answer is negative K1F CACB plus K1B CC2. Component A and B is negative because it is consumed. Meanwhile, for CCE for component C is 2V K1F CACB minus 2V K1B CC power of 2 minus V K2 CC, and the final answer is 2 K1F CACB minus 2 K1B CC power of 2 minus K2 CC. And okay, so for reaction 2 from C, we will get 2D plus E with the reaction rate of K2. So as usual, the TCE will be 0, and we need to find the CCE for each component, and now we need to find the CCE for component D. So from component D, we'll get 2V K2 CC, and the final answer will cancel the V, we will get 2 K2 CC. Same goes for the component E. The CC for component E is VK2CC, and we will cancel out the V, we will get K2CC. Okay, that's all from me. Thank you.
Hi, I'm Firdaus, and I will present an example from our batch reactor tutorial. So let us read the question on example 2. The oxidation of ethanol to form acetaldehyde is carried out in a batch reactor. To make it easy for us, we can change the notation to ethanol label as A, while acetaldehyde label as B. So the reaction will be A producing B. And then it says that unfortunately, acetaldehyde is also oxidized to form carbon dioxide. And this will add to our reaction becoming A producing B with B producing C, where C will be our carbon dioxide. It also mentions the reactions are irreversible and first order in ethanol and acetaldehyde, which means that the reaction is only in forward reaction. As for the assumption that we have in this question is volume of reactor is constant and density of solution also constant. And we also have ratio of inlet flow to volume, which means F over V, which is equals to 0.25. And here we have our concentration of A and B. And our K1 and K2 is in per unit time since it is first order. Okay. And then we need to simulate using Euler method for concentration of A and B at t equals to 0.4 minutes, having step size of t equals to 0.2 minutes, which means that we need to perform two steps of iteration. To solve this question, as per usual, let us start with writing our general equation of TCE and also CCE. For our TCE, since the volume is constant, then we can make our dV over dt equals to 0. And for density constant, we can take out the density from the left-hand side equation and cancel out with the density at the right-hand side equation by dividing it. For our CCE, like I said, we can label ethanol as component A, acetaldehyde as component B, and carbon dioxide as component C. And for CCE on A, the rate of formation is written as negative VK1CA, where for reaction K1, component A acting as the reactant. And as for CCE on B, the rate of formation is written as positive VK1CA, since B is the product for reaction K1, minus with VK2CB, and the negative symbol indicates B is the reactant. So what happened if the question want us to find the rate formation of C? Then the rate of formation of C would be 2 VK2CB. After we find our CCE, we just simply substitute the initial concentration of component A and B into DRCCE to get their rate of change, which is -2 and 2 respectively, for t at 0.2 minutes. Then, applying Euler method to calculate the concentration of component A and B for t at 0.2 minutes by substituting the rate of change that we have obtained from the previous calculation, where we will get the concentration of A and B equals to 1.6 and 0.4 mole per liter respectively. For the second iteration, we will repeat the same step, but this time using concentration of T at 0.2 minutes to find the rate of change of component A and component B of T at 0.4 minutes, where we will get negative 1.5 and 0.5 rate of change for component A and component B respectively. Finally, applying the same Euler method by using a rate of change for T at 0.4 minutes, we will get the concentration of A and concentration of B of T at 0.4 minutes to be 1.3 and 0.5 mole per liter respectively. And so what we can do is that the basic of Euler method is that we estimate the new concentration using new rate of change which we calculate using previous concentration.